So, in this week we continue looking at polymer systems of different kinds, and we have started looking at copolymers first. We saw in the last lecture how different copolymers can be used in various applications, and in this case we will look at some of the properties of these copolymers, and we will do this by first looking at quickly how do we exploit and understand the reactions of two monomers and achieve a type of copolymer that we want, whether it is a block copolymer or a random copolymer and so on. And then we will look at the behavior of copolymers, and more specifically we will look at one example of a block copolymer which has very interesting behavior, like we saw in case of silicon polyether in the last lecture on 26th lecture. So, copolymerization is a technique to make sure that we achieve a target sequence that is desired for a given application. So, the question of course is how well can we control it, and what I have shown here is let us say reaction between two different monomers M1 and M2. So, the active species of a chain which has M1 as the active species can react with M1 itself to give you M1 M1. So, this is one possibility. Of course, M1 can also react with M2 and get you an M1 M2 bond. Similarly, M2 itself can also react either with M1 or M2 to give us M2 M2 or M2 M1. So, these are the four possibilities when we think of reaction between M1 and M2. M1 can react with M1 itself, or M1 reacts with M2, and similarly for M2. Now, the question is can we control this polymerization so that we obtain, let us say, a random copolymer, in which case M1 M2 are randomly distributed, or we obtain a block copolymer, in which case M1 should react with M1 so that we get M1 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 M1, and then eventually because of statistical distribution 1 M2 will react, but as soon as M1 M2 bond is formed, now we would like M2 to react with itself. So, that if we do a reaction like this, then in that case we will get M1 M1 M1, and then after that M2 reacts, and then M2 reacts with M2 again, and then we get a block of M2. So, this is the way we can look at the control of polymerization, and the way we think about it quantitatively is look at these rate constants which are present for each of these reactions, and we look at their ratios. So, for example, reaction rate for M1 to M1 reaction to reaction rate to M1 to M2 reaction, and by looking at these reactivity ratios we can find out whether one would like to react with 1 or one would like to react with 2, what are the different rates of reactions. And this is one common way of quantifying the copolymerization tendencies. And so, in this exam question, for example, two monomers which have reactivity ratios of Ra and Rb as we just defined, when do they form? Alternate copolymer, which means it is AB, AB, AB kind of a polymer. And so, there are various options depending on the Kaa or Kab rate reactions that we talked about. All these, so basically it is an issue related to how are these rate constants, and their ratios are of course Ra and Rb. So, you can think about answer to this. I will just give you a hint related to the answer which is not there, which is let us say Ra is equal to Rb is equal to 1, in which case all the rate constants are equivalent. So, the rate for A reacting to A is equivalent to A reacting to B and B reacting to A and B reacting to B. So, therefore, if such a possibility is there, then basically any species can react with any other species, and in the end we will get a random copolymer. But in this question the target is alternate copolymer. So, what should the reactive ratios be? So, in terms of properties, when we look at copolymers are properties related to the homopolymers that are formed, and in a lot of cases there are thumb rules and rules based on theories which we have arrived at, and so therefore we can understand the copolymer properties based on what are the homopolymer properties. And the key determinant of course is also the type of sequence which is there. And so, for alternating copolymers and random copolymers, these mixing rules work very well, because you have basically a distribution where you have M1 and M2 are systematically, this is a case of alternating copolymer, or even if we have a random copolymer, since we have them randomly distributed, we can again have, so this is a random copolymer. So, properties of these kind of copolymers are easy to determine based on our knowledge of the homopolymers. And here one example is given for a glass transition temperature, because if the question is, if we know the copolymer glass transition temperature, can I find out the copolymer glass transition temperature? Now, before I give you this example, you can think of why is it that I have not included block systems in this. So, if I have, let us say, a block of M1 connected to block of M2, why is it more difficult to predict the property of copolymer based on the knowledge of homopolymers? And next slide, when we discuss an example of block copolymer, hopefully the answer will be little more evident. So, let us continue looking at glass transition temperature of a copolymer. We have already seen in the lectures related to glass transition, the 22nd, 23rd lecture, that we have free volume theory which can be used to describe glass transition. And we know that this free volume is known for let us say the homopolymer 1 and 2, and here what is shown is free volume for homopolymer 1, and so it depends of course on the glass transition of polymer 1, and so similarly there can be an expression for the free volume of homopolymer 2. So, now we have these two monomers combined together either in a random or alternating fashion, and so if we make an assumption that whatever is the free volume of 1 and whatever is the free volume of 2, they combine each other in an additive fashion. So, that in the final copolymer, the free volume of 1 weighted by whatever is the weight fraction of that homopolymer, and similarly free volume of homopolymer 2 weighted with whatever is its weight fraction. So, if we do this, and if you go back and look at the free volume and how we derived the WLF equation and the overall dependency of properties around glass transition, these assumptions can immediately lead to the copolymer being a simple mixing rule. So, the copolymer will be closer to the polymer which is in larger amount, and this is just a linear relationship between the homopolymer glass transition temperature and the copolymer glass transition temperature. So, using mixing rule like this, we can actually estimate the properties of copolymers and also understand the properties, and this is also useful in terms of targeting. So, if I have let us say two homopolymers with glass transition temperature of -80 and -10, and it is my target to achieve a glass transition temperature of -40 degrees, using such thumb rules I know what kind of relative ratios to shoot for in terms of synthesis. So, generally this combined behavior for such polymers can be obtained by knowledge of homopolymers. So, if molecular flexibility also can basically be a combination of the flexibility of the two repeating units. Similarly, the size in terms of the radius of gyration or end-to-end distance. Key of course is also the intermolecular or intramolecular interactions. So, depending on the hydrophobicity, hydrophilicity, or hydrogen bonding potential, or electrostatic interactions, or any of the interactions that we discussed in the 20th lecture, if we have differences in the two monomer units or the two repeating units, those can also get basically combined effectively to get us an effective property for the copolymer. Same is the case also how solvent interact with the macromolecule. In case of crystallization, there is interesting possibilities, and let us say that we have M1 and M2, the two homopolymers, and we are combining them, and let us say M1 is crystallizing. If we have a random copolymer, then of course clearly we will not be able to crystallize, because it is essentially, if I just draw it using a if we have some polymer like this, then there is no way we can have M1 organizing with respect to each other, because M2 will always come in between. But if we have certain, it is a random copolymer and there are few places where there is M1 combining with M1, and there is another macromolecule or another part of macromolecule, and again M1 is combining with M1, then there is a possibility that there can be organization of these M1 chains. So, effectively if we have a copolymer of M1 and M2, while it is being cooled from the melt state, what needs to happen is demixing. First, part of M1 and M2 need to separate out from each other, and then M1 can have a chance of the formation of lamella and crystallization. So, the impact of copolymerization on crystallinity is quite complex, and it depends on specific systems. So, let us finish this lecture by looking at an example of a block copolymer. Block and graft copolymers are quite commonly used in several biomedical applications, and the idea here is again exploiting the properties of block themselves, and these two blocks have a contrasting set of properties. So, in this case we will also see, when we discuss polymer blends, the miscibility is similar. The way we think of whether one block is mixing with other blocks or do the two blocks phase separate out will depend on when we mix the two polymers in the form of polymer blend. So, let us say if we have one polymer and another polymer mixing with each other, there is a possibility that all the blue macromolecules would like to be together and all the black macromolecules would like to be together. Then we call it an immiscible blend. So, similarly in case of block copolymers also, if we have a block of these homopolymers attached to each other, then what we can have is all the similar interaction blocks will come together, and in the end what we get is a domain of one type of blocks in combination with another type of block. The only difference between the blend situation and the copolymer situation is the fact that the blocks are combined using a covalent bond with respect to each other. So, clearly the domains that are formed in this case depend on the block length. So, therefore, block length is a very key determinant of the microstructure of block copolymers. And this is the tunability that is being exploited when I said that block and graft copolymers are very commonly being researched as well as used for variety of these applications. By changing the block length, you can change the properties very suitably and therefore obtain different types of performance. I will just leave you with one example of biomedical applications of a set of polymers which are called polaxomers, or they also are available as registered trade name with pluronic, and they are blocks of polypropylene oxide in the center. So, we have polypropylene oxide block in the center, and then the blocks of polyethylene oxide on the two end, and which is what is depicted here, where there are basically blocks of red blocks surrounded by two black blocks. And this kind of a material system has very interesting properties, because at lower temperatures basically all these blocks are randomly oriented, and therefore the system is molecularly mixed and it is a solution. Once we increase the temperature, what happens is all the red blocks get together. So, polypropylene oxide blocks get together. So, what we have is basically the blocks arrange themselves so that polyethylene, which is more hydrophilic, starts interacting with water more strongly, and polypropylene, which does not like water as much, would want to cluster together with each other. So, therefore, we get what is called a micelle, very similar to surface active agent surfactants giving us micelle. And more interestingly, if we increase the temperature further, then many of these micellar systems form assemblies where you get a gel like response. So, because of this interaction between the blocks and the surrounding solvent water in this case, we can have a solution or we can have a micellar solution or we can have a gel, micellar soft solid. So, you can see how copolymers in this case can give you very different properties if we just change the temperature, and look at the temperature here, 37 degrees Celsius. I do not know if anything strikes you in terms of temperature of 37 degrees and biomedical applications. So, if you just remember, our body temperature is just above this kind of temperature. So, if we tune this transition point very well, what we can do is one state when it is stored under refrigerated condition, because then the temperature will be much less, and as soon as it reaches our body, it reaches another condition. So, therefore, these kind of block copolymer systems can become gel when they are injected in the body at 38 degrees Celsius, but they will remain in perfect liquid like. So, therefore, you can inject them easily. So, you can see these are examples of smart polymeric systems, and in this case the smartness is achieved because of interactions of two different blocks. And clearly, if we vary the lengths of these blocks, we can vary the micelle size, we can vary how the gel is obtained, what is the temperature at which gel is obtained. And so, this is the strength of polymeric materials of different kind, where by tuning physico-chemical details at the macromolecular level, we can achieve performance at the bulk scale. So, with this we will close this lecture. Looking at the answer related to copolymerization, I am sure you have been able to see that if we really have to get an AB-AB, which is the alternating copolymer, then the rate of reaction of A to A needs to be much less compared to the rate of reaction of A to B. Similarly, the rate of reaction of B to A needs to be much more than reaction of B to B. So, therefore, then BA bond will preferentially form and AB bond will preferentially form, and then of course, that will imply that we will get the alternating copolymer. Thank you.